Okay, today I'm going to talk about wind design. Wind design, for wind design, you need to have knowledge of aerodynamics first. It's very complicated, but I'm going to try to give you the basic information that I think is necessary for understanding of the wind design code provisions. And also, definitely, you got to understand the structural dynamics, the dynamic responses of high-rise buildings subject to wind forces. It's a similar to response to earthquakes. That is called resonant component of the wind forces. And also, we got to understand the characteristics of the wind itself, as well as the aeroelasticity. When you do wind tunnel test, we typically use rigid model so that we try to capture the aerodynamics of the basic wind speed, and then the pressure responses, and also base, shear, and twisting moment responses, so that we don't really consider the structure behavior during the wind tunnel test for aerodynamic wind tunnel test. But when you have a flexible model, the structure is also moving subject to winds, so that its behavior is also considered during the wind tunnel test. That's called the aeroelastic wind tunnel test. But it's a little tough to perform because you got to have scaled mass and stiffness in that model. Which is realistic, which is close to the rear building, which is scaled, so that we typically perform aerodynamic wind tunnel test. Okay, either for the measurement of the base shear and twisting moment at the base, or the wind pressure at each location of the facade, front face, leeward face, and then side walls, and so on. It's the most accurate you actually perform wind tunnel test, but for regular structures, for low-rise structures, and also the mid-rise structures, we want to calculate the design wind forces without performing the wind tunnel test, so that you can go forward. You can move on to the preliminary design of the structures. Without having structures, how can you do wind tunnel test? So we need to have some kind of wind load provisions. That I'm going to teach from now on. And even for high-rise buildings, you got to compare that the wind tunnel test reserve in comparison with the reserve from the wind load provisions. Okay, so somehow we got to understand what's going on in the wind design code. Okay, so introduction to wind design. The reference is Korea Building Code, which is similar to international standard organizations, the code, but it's very different from the US code, ASC 7. Okay, so but anyway, its basis is on the theory that was developed by Professor Davenport. So as long as you understand the fundamentals Probably it's not too difficult to understand the Korea building code by looking at the equations. Of course, notation symbols are different, but I'm gonna try to explain what that is when it comes. And also, those notations are very different from those in Chopra's textbook, Dynamics of Structures. So this is unavoidable, and I'm going to try to explain each notation every time in each slide. So first, understanding of a wind load. Understanding of a wind loads, characteristics of a wind loads. Okay. Wind load consists of a mean and gust component. When you see this, a time history of a wind speed, the average of a wind speed for a certain duration, for example, here, it's 10 minutes, 600 seconds. It's a 10-minute average. And then black solid line represent the mean. And that's almost like a pushing force to the building. So it's more like a static force. And there's a variation around that mean wind speed. And that's obviously dynamic force. And by this dynamic variation of a wind speed, structural response will be dynamic. So when you consider seismic laws, ground acceleration histories will have the energy in high frequencies, like greater than 1 hertz, more like in between 1 to 10 hertz. So that affects low-rise buildings' response a lot. Conversely, for high-rise buildings, the seismic actions of the ground will not affect that the high-rise building response that much. So it's more like in this range. Wind load, there's a lot of frequencies here. Well, here it's like very very small frequency with a large period. But right there, you see that a little bit higher frequencies. And overall, its energy contents are focused on much lower frequency range compared with the seismic load spectrum. For example, 10-story building. 10-story building, we assume 1 second period. And 1 second period is same as 1 hertz. So 10-story building, it's not vulnerable to wind load because anyway, your wind load energy content will be smaller for that frequency. 10-story building, you will be affected by the seismic load larger than the wind load. For 100-story building, depending on the stiffness and mass combinations, but its natural frequency is more like closer to 0.1. So its energy content of a wind load is significant compared with this energy content at the frequency of 1 hertz. So it affects a lot. And that's only the wind speed spectrum. And dynamic amplification in that frequency, 0.1 hertz or similar, it's going to be much higher. So high-rise building is vulnerable to wind load rather than the seismic load. Okay, the bottom graph, that's power spectral density distribution. Power spectral density means underneath that graph, the area is the same as the standard deviation square. So, well, you have a peak wind speed over there, but also you have a standard deviation. I don't know the value, say that's a sigma. And energy content here, actually here in this range, that's going to be same as a sigma square. Okay, so that's a power spectral density's characteristic. And for the mean force, well, this time history here has a mean wind speed of say 17.5 meter per second. That lasts very long time, maybe an hour, maybe 2 or 3 hours. So then its a period is maybe 6 hours or 12 hours. Very low frequency, very large period. So that's why we call that it's almost static. So in this range, it's more like a static force. And see, this frequency is not the same unit here. It's not hertz. Hertz is a number of a cycle per second. This is a number of cycles per hour. So you gotta convert that unit here, the value here, to get the value in the below graph. If you convert that, you will realize that that peak locates right over there. Okay, and we call that gust. Gust is the variation of a wind speed around that the mean wind speed, and peak value is much greater than the mean plus 1 standard deviation, maybe mean plus 2 or 3 standard deviation, and then the mean minus 1 standard deviation. That's not that important value because it's more like a lower bound of the mean speed, lower bound of the wind speed, and we are more interested in peak value. So later we try to get the peak value of a wind speed. You know that the pressure, according to the Bernoulli equation, if velocity becomes 0, then the pressure applied to the obstacle will be 1/2 times the air density times the velocity squared. So we're interested in finding out the mean velocity because that's going to be transformed to the wind pressure, and then integration of the wind pressure will be the mean wind force, or maybe peak wind force. So we're going to learn about that. Okay. Anyway, the gust, those frequency contents for the gust is very large, the period-wise, and very small for the frequency-wise compared to seismic load. So wind loads, first of all, the wind speed matters, so that the higher wind speed, of course, you have a higher pressure, like here. This is from the Bernoulli's equation. You know, the velocity becomes 0, then it's all change. Well, if it's a building, it's really, really large, then center, the fluid cannot go further, and then it stops with 0 velocity, then it just transforms into the pressure. So this is from the Bernoulli equation. And rho is air density, 1.22 kilogram per meter cubic power. So wind speed affects the wind loads. But then you just saw that the wind load is very irregular and it's a random. So we need to use some kind of random vibration process to get other parameters like mean, standard deviations, and so on. And then gust is also called turbulence. It's not steady. Okay. Unlike seismic loads, wind loads have strong, long period component. I'm talking about gust. Gust has a long period component. Mean, very, very long period component, okay? Anyway, this kind of a long period component is kind of a critical to high-rise buildings. So factors affecting wind loads include wind speed, turbulence intensity. You have a large variation. Then you have a large turbulence intensity, okay? Topography, on the hill, you have a higher wind force because of accelerated wind speed. When you have a slope, ramp. And then surface toughness, well, if it's an ocean, in the middle of ocean, or maybe in the coastal area, you have no obstacles in front of the building. Of course, wind speed is much larger. And if it's inside the building forest, like in metropolitan area, then already wind speed is much reduced. So surface roughness is involved there. And then building itself. Shape is very important. That's a difference from the seismic engineering, earthquake engineering. Because that's not structural dynamics, that's more like aerodynamics. So that corner of the building plan, if it's a sharp, you're actually creating a lot of the wind forces. And if you have a taller building, of course, that's related to aerodynamics, because it goes like this, and also structural dynamics, like the natural frequency is related to that height. So the period, also the natural period, is heavily related to height of the building. So these are the components that affect the total wind loads. Okay, first, wind speed. Wind speed is consisting of mean component and then fluctuation. We call that gust. Okay, fluctuation. And components with the period larger than 10 minutes or 1 hour, like this is lasted about 10 minutes or maybe an hour, and then it becomes smaller, like almost zero. So it's not a matter of 1 minute or so. It's for the long duration. Again, wind load, wind-induced pressure to the building is called wind velocity pressure. Okay, actually it's a pressure, but then the name is a wind velocity pressure. And then if we use mean wind speed only, not peak, not the peak, but mean wind speed, and then it's called mean wind velocity pressure. It's pressure. Mean wind velocity pressure. In the code, that terminology is used. This is a mean wind speed or velocity, and this is if this is a mean wind speed, this is a mean wind velocity pressure. Of course, in the other planet, density of air is different, but on Earth, this is same everywhere. That's pretty much equal to any country. Okay, no discrimination. 1.22 kilogram per cubic meter. Next, affecting parameter, surface roughness. Well, because of a friction, wind speed profile is not uniform. Rather, it's exponential. Okay, so at the surface, wind speed is 0, so almost no wind, and then it increases exponentially, and it becomes constant all the way above certain height. Well, it's not really straight. Okay, like this. And that layer is called boundary layer. Okay, atmospheric boundary layer. Okay, ABL, atmospheric boundary layer. And then above that is almost constant. Okay, so gradient of the wind speed profiles affected by the surface roughness. Coastal area, of course, is very large. Then inside the land, far from the coast, it's large. And if you have a city, very large. The roughness is very large. And if it's suburban, so smaller. Okay. Next, turbulence intensity. Turbulence means variation of the intensity, so that you have a large variation. For example, near the atmospheric boundary layer, maybe your wind speed profile, if it's time, maybe means wind speed is high, but then it changes kind of a small. Okay, but then near the ground, mean wind speed is not too large because of see, it's not too large compared with this. But then you have a large variation, maybe. Maybe my drawing's not good. Okay. And maybe it's negative. Okay. Well, I'll say it's absolute value only. Okay. So we don't care about the vector. We care about the speed. Okay. A large variation. So then you have a large intensity, turbulence intensity. Then I is used. Turbulence intensity is a factor to indicate intensity of a fluctuating component of a wind speed. It's just that standard deviation from the mean, you have a certain standard deviation. Standard deviation is very small. But not only the standard deviation of the wind speed, normalized by the mean wind speed. That's called turbulence intensity. Okay? So it's nothing else other than the ratio of a standard deviation and mean of a wind speed. Turbulence intensity is one of the indicators for estimating the peak value. Of course, if you know the standard deviation, that's a good representation of the peak, right? If you have a larger standard deviation, of course, peak will be much far from the mean. Turbulence intensity is strong, as I said. Even though mean is smaller, standard deviation is large. This is small, this is large, so the intensity is very large compared with that higher location. And why? Because you have many obstacles Sometimes it's obstructed by nearby buildings, forest, but then sometimes it's not. So then you have a large variation. Okay. So turbulence intensity, that's a variation of wind speed, so that wind scale is a larger at upper stories, like a higher, the location. But then variation is smaller at higher, at larger height. The turbulence scale is smaller near the ground, but then variation is quite large. So you got to remember this curve. It's inversely proportional, not linearly proportional, but exponentially proportional for that turbulence intensity. That's because you have a large variation at the ground level, but the turbulence scale is large at larger story. And depending on the roughness, like a city location, the downtown location, you see that the intensity, turbulence intensity is getting larger. But for roughness C, which is in the open terrain, turbulence intensity is not that large. It's very consistent. The turbulence scale is large, but then there's a slight variation with respect to the mean speed. Suburban area is defined as a roughness B category. So, I mean, in this graphical presentation, you can get a sense of turbulence intensity in the scale. Next, topography. So, as you know, on top of the hill, on top of the ranges, there's accelerating effect for the wind speed, so that up on the hill, escarpment, you got to consider that the larger wind speed. So there's a factor for that, separate factor, topography effect factor. Okay. So it's nothing serious. Next, building itself. When you have a windward face, of course, this wind speed becomes zero right there. Of course, at the side, of course, it goes around there, but in the middle, maybe it just stop there. So then it's transfer to pressure, positive pressure, we call that. And then leeward of the building facade, you see a little bit of suction. So then, by the wake, there's a negative pressure. And of course, this pressure times the facade area right there, plus facade area here times the negative wind pressure is the total wind force along this line, and that's called along wind direction. Okay. Anyway, we gotta know that there's a negative pressure in the behind the building. In addition to positive pressure on the front. And also you see when it's go around the corner of the building, it's detached from the building. Then actually it has it's not moving straight, it has a curved movement. That is called vortex. And especially for slender building, this kind of a vortex shedding is like this wave happening, sequentially on each side of the building in a regular period, so that it's related to the aspect ratio, building height to the dimension of the plan, also shape of the building. If you have a sharp corner like this, it's not good. So that this vortex is shed alternately at each building corner. That way, actually, you actually shaking this building in the perpendicular direction to the along wind direction. That is called a crosswind load. And also, because it's not symmetry, you push right there by this vortex shedding. And then, right after that, you have that kind of a force in the other side. So that causes more like a twisting of the building. And that kind of effect we gotta consider. And then when we express that as a static wind load, that is called torsional wind load. So this kind of the effect, this kind of effects depend on height of the building, size of the building. Aspect ratio is height to dimension ratio, shape of the building, rounded corner is much better in terms of this, and sharp corner is dangerous. Also, buildings' own dynamic property, natural frequency, slender building, you have the smaller natural frequency, then it's likely to have vortex shedding. Wind loads include components with a wide range of frequency, as you've seen in the previous slide. Frequency content, frequency contents are more like this, and then, my drawing, it's just rough sketch, okay? And then your building frequency maybe located somewhere here or there, okay? Say this is power spectral density. And typically normalized power spectral density is used, but let me talk about that later. Okay, and then also this kind of a contents, because you have a certain contents, because if your building is located right there, maybe you have a zero contents from that wind, then you have no dynamic effect. But for anyway, this tall building, you have a certain frequency contents in that wind, so that it creates some kind of resonant effect. Of course, if you have no damping, it's going to be infinite, but you have a damping, anyway, there's a amplification, certain amplification. Okay, that's the same as a seismic load. So in the building code, wind load code provisions, they adopt the method of gust load factor method. You know that the mean wind speed from the statistics of previous measurements, and then it's standardized in the code. And you know the wind profile, vertical profile, that's determined from the mean wind speed and then the surface roughness. Sometimes topographic effect is involved, like up on the hill, escarpment factor should be applied. Also, so vertical wind speed profile, vertical profile, you know that the wind velocity pressure, it's just pressure, 0.5 times rho v square. Rho is what? Atmospheric air density, 1.22. And then the 0.5 v squared. So the pressure, mean wind velocity pressure profile also you can get. Then also you just integrate that the total of pressure over the area of the building, facade area of the building, you get force, right? But that's only for the mean. You got to consider the gust effect. And you just apply the factor, like a factor. Say this is a mean, okay, so this is a mean pressure. And then you multiply by certain factor, because you know mean, and then you know standard deviation, and then you know peak. Anyway, it's offset from the mean. It's offset from the mean. So say this is a v, pressure, the velocity, time. It's offset from the mean. So somehow peak is certain factor, say g, times the mean velocity. Then you may have peak value. So that gust law factor, well, this is a peak wind speed, but it's a square root and then multiply by area, then you will have a force, mean force. Okay? Apply to the building. So if you multiply by factor, say g, you will get peak wind force, similar to base shear. That is called gust load factor. So this kind of approach is applied in the design code. But then this is not all. You have another factor, which is resonant effect. Not only the peak value, there's also amplification by that dynamic input. So that is also expressed by the gust law factor. However, that's not really accurate method to reflect the real dynamic behavior. But anyway, the code provision, most of the code provisions adopt this method. Korea building code. Okay, the diagram looks a little complicated. Let me just follow what's in there. First, you have a measurement, and that weather station, which collects the wind speed, is not always at 10-meter height from the ground. when we call basic wind speed, mean wind speed, that is in reference to the 10-meter height from the ground. When you say, okay, Busan area, Haeundae area, I have a mean wind speed of, I don't know, maybe 30 meters per second. That means 10-meter height of that site. But when we measure, it's not necessarily 10 meters. It's different, okay? Then, first you have a measurement here, and then you know the distribution. You know the distribution of the wind speed profile, which is dotted line. So you try to predict the from the measured data, you try to predict the wind speed at atmospheric boundary layer. Okay, atmospheric boundary layer. It's the region. It's the height where you're gonna have a constant wind velocity above that layer. That is ABL. So ABL is right there. ABL, atmospheric boundary layer. Okay. So then you predict that value. Maybe it's right there. Okay. So from the profile, and then that profile is the function, exponential function with the power of alpha. Okay, power of alpha. Okay. So dotted line, kind of from that surface with that roughness of, say, D. I'm sorry, not D. Yeah, D. Yeah. Okay, D. Roughness D. Okay, and then because above the ABL, the wind speed is assumed to be same, even with the different surface roughness, because it's the same time. Just imagine that you can remove all the buildings, all the hills, all the forest. I'm like a god. You can change the wind surface, but same wind. It's the same wind. So anyway, above the ABL, it's the same wind force. And then you apply that wind speed to roughness category C. Okay, roughness category C. You try to modify that so that using that the solid line, you know the distribution, and you try to find the value at the 10-meter height. You can track of these wind speed. Anyway, wind speed profile factor anyway is related to wind speed. Okay, that way you can give general 10-minute average wind speed, normalized wind speed for every region. Every region, if you say wind speed, mean wind speed 20 meters per second, and then in the region B, A region, you have a 20 meters per second, and then B region, 20 meters per second. Anyway, wind characteristic is the same. Of course, A site you have the very rough surface roughness. B maybe not. Then you will have a different factor. But when we talk about average wind speed, it's based on roughness category C, and then at the height of the location, height of 10 meter. Of course, measured data are from everywhere, but you normalize this so that every time when you talk about mean wind speed for the duration of 10 minutes, it's based on roughness category C and height of 10 meter. Okay, anyway, and then you have you want to know really the return period of that wind, right? You measure that wind speed, which is during the typhoon, and it's large, but you don't know, that much of a size of a typhoon comes, what kind of a frequency, what kind of a period. So using that Gumbel distribution is kind of a probabilistic approach. You can predict the 100 years, 100 return periods wind speed. Okay, so that we have a wind speed, and then you measure that for the certain cycle. Say 5-year cycle, you measure this wind speed during the 5 years. Then, how can you predict the mean wind speed for the duration of 100 years? The probable wind speed that you're going to see for the next 100 years using the Gumbel distribution. That's how basic wind speed map is formed. Okay? I don't know if I explained that the basic wind speed map construction, but it's from the data, and then that is a transfer to the data, assuming that you have a roughness category C and height of 10 meter. But then that is a measured only for short duration, and you want to calculate the wind speed, assuming that you have a 100-year return period. That is on the map. So this is already determined by the experts. Basic wind speed at specific site is available. Okay, what is a roughness category? It is defined as an open terrain with scattered obstructions with heights of 1.5 to 10 meter or so, or scattered low-rise buildings. It's more like a suburban area. So this is a mean wind speed or basic wind speed map of Korea, South Korea. It gives you 100-year return period of 10-minute average wind speed. Okay, I just combined these two. And with the assumption of a roughness category of C and the level of a 10-meter height without any topography effect. So if you there's a site, this kind of a site, and then there's a little bit of a hill like this, so that it's higher than the other area. For that site, I have a same 100-year return period of 10-minute average wind speed. I don't know, maybe I can pick up 36, very high, 36 meters per second. Okay, But then right over there, I have a topography effect. So I gotta apply topography factor. So it's gonna be larger than 36 compared with this location. Okay. Say that location, even though it's the same area, right now I have a coastal line like this, so that I have a surface category B, but it's here C. Well, this wind speed is for the assumption of C. So when you try to calculate B, you gotta apply that surface category B. Okay, so that it's going to be higher than 36 meters per second. Okay, that is shown right there. So basic wind speed is just a statistical representation of the wind speed for that region that you're going to see during the 100 years. Okay? But then each specific site and each specific building, your design wind speed will be different because it's up on the hill, so it's larger than down on the hill. And if you try to build the building very high, your design wind speed is very large compared to the building right next to that. You build this much, then roof level speed is smaller, even though it's the same site. So design wind speed is related to the building height. The definition is wind speed at building height, roof level. So that's defined as a VH. And this VH should include topography effect, ZT. Well, every code has different notation, but in KBC it's a ZT, topography effect factor. So right there, it's a different. And then height, depending on the height. Well, in this case, because it's on top of the hill, actually the VH is larger for shorter building than this. Yeah. But when you just talk about this height, this location, if you want to build this building and then this building, KZR is different. Okay, KZR is just the profile, the wind speed profile. So KZR times V0 is really the profile. V0 is not the profile. V0 is one value at one site, at a site. So the profile is really the V0 KZR. So then you have a wind profile. Okay, this is just a factor profile, but it's the same shape as V0 KZR. Okay, and then importance factor. If you're building, so federal building, high-rise building, like school, hospital. You're gonna apply importance factor higher than the other, just like seismic code. So once you have design wind speed, which is the wind speed at the roof level of the building, you can calculate design velocity pressure. Okay. V0 was mean wind speed, average wind speed. This is a average wind speed. 10-minute average, okay? For the US code, actually they don't try to get 10-minute mean wind speed, rather that they try to get the 3-second mean wind speed, which includes gust, okay? So 10-minute average wind speed, that's this. And VH is, if you have a importance factor 1, if you have a noise Kalman, it's just the roof level wind speed. Design is called design wind speed. And design velocity pressure. That's the pressure at roof level of the building. And below the roof level, it's going to be smaller than that. Wind speed profile factor, as I said, that's just having this kind of exponential shape. At that site, you have a basic wind speed, and then you're going to multiply by wind speed profile factor, okay? It's exponential function with the power of alpha, okay? Okay, so all right, so the next line, well, load profile, okay, load profile. Of course, you know, V squared, you know, V, it's going to be pressure. It's going to be pressure, and then multiply by the area. Then force will be V squared, so that it has a load profile will have the power of 2 alpha, yeah, because it's square, okay. Anyway, here, KZR, say our site is a surface roughness category C, and okay, so that V0 is maintained above atmospheric boundary layer, so that, well, it's a multiplied by 1, okay? This is 1, KZR, okay? Well, this diagram is wind speed profile. And then it's reduced and then becomes 0, okay? That is V0 times 0.71 Z. Z is the height to the power of alpha. Okay? Surface category C. That's the wind speed profile. It's not looking like an exponential function like this. And then, not exactly 0. Up to 10 meter height from ABL to 10 meter. You follow this expression, ZB. ZB is at 10 meter, which is the point where you're going to have a constant below that. Surface category B is going to be changed to 15 meter, and then A is going to be 20 meter, okay? So that it's really that distribution. And atmospheric boundary layer height is also given in the code. So that's 350 meter. And this distribution, that function here, alpha, that alpha is 1.15. Okay, that's from the code. Right?